you set eta in that way, then this term is upper bounded by this. Okay? And you can get upper bounded by this. Now then, so we've found sort of the convergence rate for, so we know the convergence rate for ellipsoid algorithm, okay, which depends on the ratio between the small ball and the big ball, and also gradient descent. Okay, we know the gradient. And we're sort of comparing. And I've already mentioned this. Let's say you had a date, I sort of talked about this, separating plus or minus by a hyperplane. Okay, so here separating the blue, which has label 1, and the red with label -1 by a hyperplane like that. Okay? Now if the hyperplane, if the line is correctly placed, that separates the plus ones from the minus ones correctly, then this condition is satisfied. Right? And I mentioned this, right? So that you take, this is the direction of W. Okay? You take the inner dot product with this blue, some positive value, then you multiply by the label, which is plus, then it takes the positive value. So that's, for these values, W is this way, the point is here, you take the inner dot product, you get a negative value times its label -1 gives you a positive value. So for red and blue, this condition is satisfied. Okay? I'm going to normalize the data for all I. Okay? Normalize it so that all of them are within the unit ball without loss of generality. And I'm going to also define this gamma to be the minimum value of this. The minimum value of the inner dot product with hyperplane and data. Which data would give you the smallest, this value? Which data would give you the smallest one? Do you know? Which value of here would point to this same verse? This is either plus or -1. Which one would give you the smallest? The one that is closest to the hyperplane. Okay? That will give you the smallest. Okay. So if I was to use the ellipsoid algorithm, how do I start? I say, oh, is this in C? This is the feasibility, right? Ellipsoid. Is it in here? And the oracle says, what oracle does is takes this W and checks this. Okay. Then is WT in C? If this happens, if W does this, is it in C? No. Right? If it's in C, all of this has to be what? Positive. And look, it goes through all the data, and says, oh, there's one that it's not satisfied. So it's not in C, right? Then what is the W? Then what is the vector? What is, so the oracle, in the ellipsoid algorithm, it checks, and then if W is in C, then you're done. If it's not, then it has to give you sort of a vector or some value, okay, which you can update. And what is that? The oracle returns actually the subgradient, okay, of. So what is our function? I take the derivative of that. What do you get? y(i)x. That's what it returns. For incorrectly classified data. Okay? And with that, so this is the new V. With that, you can update your W and also your A. And after this many iterations, what happened? Y is 1 over gamma. 1, because we've normalized all our data. The big R is 1. Okay? And the hyperplane that's close. So for this data, which one is most difficult? This one is difficult to classify, right? This, and that value, for that value, the smallest, actually this is called the functional margin. Is another word. I'm going to talk about it later on, and when I'm talking functional margin. Functional margin. Is gamma. So you know that at least a small that is closest will give the largest, that one. Let me just check. It takes this small r. The small r is gamma. And check on this. And it takes this many iterations to satisfy, to separate blue and red. And using the subgradient, where I have done this, you minimize the same thing, but you minimize this function. The function is the maximum value of the negative. I've talked about this, right? When I was talking about the intersection of C's. This is the negative value of, so you want all of them to be minus a negative value. But if I take the max, if I want to minimize the maximum value of this, what would happen? So if it's correctly classified, what is this value right here? Positive. Negative value. So I don't really have to worry about that, right? But if it's incorrectly classified, then what is this value? Negative value. Minus. So it's positive value, right? I'm looking at worst case, And I want to do what? I want to minimize that. You understand this? So for incorrectly classified data, this will be a negative value. Minus minus, that's a positive value. So this would look at incorrectly classified. Worst case, incorrectly classified. And it would try to minimize it. Okay. And I should also say this. In order to use gradient descent, it's very important to have convex. You also want Lipschitz. Okay. What kind of a function is this? In terms of W, a linear function? Is that a convex function? Yes, it is. Okay. If I take the maximum of the convex function, what is that? That is also a convex function. Okay? So, it's a convex function that we're looking at. Okay? And the subgradient, if I take the derivative at W, then you get that. For some I that's making this thing really big. Okay? Because it's looking at all the W's, all the I's. It's looking at the worst one, and then you're going to take the derivative. Okay, so it's the subgradient of F will be the data that gives you the maximum of this value, and you take the derivative of that. And actually, this F is one Lipschitz. Okay? It's a linear function. It's one Lipschitz. And at the maximum point, this value will be negative gamma, because we said the minimum value will be gamma. Okay? Negative gamma. So, looking at this subgradient descent algorithm as a feasibility problem, where you want to do this. Remember I said this. Is less than 0. Okay? Feasibility, remember? I want my W to be near this value, at least gamma distance away, right? This would take at least gamma squared over 1 iterations. Why? If you can tell me why, then I will understand that you've understood everything that I've said so far. It's going to give you the solution at least gamma squared over 1 iterations. If you can tell me this, I will give you, everyone's looking at me, 3 points in the midterm. Three points. It's not difficult. After this many iterations, we're doing subgradient descent. Just look at it, the notes, what I've said so far.
원리슈츠라서 랩실은 빼고 나가서 원칙은 강남 스퀘어분의 1이고.
Very good. Okay, good. Epsilon is gamma. Gamma. Okay. It's one Lipschitz. And what was the iteration? Let's have a look. We went through this proof right here, right? Where was it? I've mentioned this. I've focused on this right here. Or right here. One Lipschitz. So rho is 1. What is epsilon in our case? Gamma. And we usually put a bound on this. So it's gamma squared over 1. At least gamma squared. Very good. 이름이?
여현호.
어?
여현호.
여?
네, 현호.
Yeah. Okay. And that sort of leads to, okay, and this later on we'll learn. It's similar to batch perceptron. Okay, and it's trying to minimize the. What error is this trying to minimize? Actually, it's trying to minimize this, right? And this is how the algorithm goes. You start with 0. You look at all the training data and check whether it's positive or negative. If it's negative, what happens? It's misclassified. It's misclassified, right? And then how do you update? You do this update. And I've removed EDA here. Oh, why did we eliminate EDA? That's the question. Why did we eliminate EDA? Who can tell me? I will leave it as maybe an example. Or the person who's scribing this would have to tell me why EDA was not included in that. Okay, I'm going to move on to the next slide. Comparing ellipsoid to subgradient. Now, this is an old algorithm, but you know it's an incredible algorithm. It's complicated, but it's good. So for if the function is convex and rho Lipschitz, ellipsoid subgradient has this many iterations, require this many iterations for convergence. And at each iteration, the subgradient would require D proportional computation. Why would you require D? D is, by the way, the dimension of the data. Dimension of the data. Why? This is sort of the computation. Subgradient. And you assume that you know what the gradients are. Because you have to add two numbers of n dimension. Okay? So that would take about n order. Whereas for ellipsoid, if you look at the computation, it's much more complex. Not much more, but d squared. Okay. Now, so you can see that the subgradient method is not the iteration is not a function of the dimension, which is very good. It's not a function of the dimension. Okay. Whereas ellipsoid is a function of the dimensions, squared. Okay, so if you have big data means high dimension and also lots of data. Ellipsoid is no big. Whereas for subgradient, it's alright. If you want it really, really accurate, this would require more iterations because this is a log of over 1 over epsilon, whereas this is just epsilon squared. Okay, so ellipsoid may be a little better, but definitely at each iteration, depending on what your dimension is, ellipsoid takes more. This is the case when you use a particular function. What was the function? It's W inner dot product of the data, right? That is, what case is that? That's F convex with 1 Lipschitz. Okay? Then you get this type of performance. Okay. So, I should also like to say that many of you probably thought, oh, convex, if the function that you're trying to minimize is convex, then surely it must be path learnable. So if f is convex, then path learnable. What is path learnable? The function value that you have and the minimum W. Also, this is the loss function, sorry. The loss of all should be within delta. Okay. Actually, do I have? What is path learnable? That your loss function has to be the test loss or the risk, let's just call it, for all W in the hypothesis space that minimizes it. It has to be within epsilon. And what? Is that it? Path learnable? It's probably approximately correct. It's approximately correct, but with what probability? 1 minus delta. When? What is the condition? This is true with probability 1 minus delta when our data is at least bigger or equal to the n. And that n was the sample complexity, right? Okay, everyone understand that? This is path learnable. Now, so this is an example that was given. I'm going to sort of go quickly. Okay, here it is. You tell me why this So the point here is that it's not path learnable. Okay? Tell me what needs to be corrected. So H is all real. Okay? And your loss function is this thing. Y is the label. And your prediction is W times X. So it's just scalar, one dimension. You give me an X and I multiply my W on it. And that would be my prediction to Y. And this will be my loss, squared loss, okay? Which is a convex function, okay? Now, let's say I have an algorithm, some algorithm, ERM, maybe one of the algorithms, or SRM, structured risk minimization, which looks at the confidence interval as well. Okay? Let's say you have an algorithm, and you assume that it's path learned, okay? And you have it. And you choose epsilon to be 1%, okay? And you choose that this path learnable to be correct half the time, 50% of the time. So that's a very loose condition, okay? Loose condition. 1%, you want it to be close to 1. And I'm just going to give you this mu that I'm going to use for the data. The mu is some constant, log of this number, divided by 2n. n, by the way, is the number of data. Okay? So if I have 1,000 data, then it will be divided by 2,000. Okay? Okay, so we have that. And let's say I have two distributions, D1 and D2. So this is how data will be generated. Okay? There are two cases. There's D1, there's D2. And I have an algorithm, square. So D1 has only two types of data. 1, 0, okay? It's all 1 zeros, or mu minus 1. Okay? And in D1, you get this type of data with probability mu. And probability of 1 minus mu, you get this data. Okay? That's D1, coming from D1. Some source. Okay? This other source only gives you this. Only gives you that. Okay? It's D1 and D2. Okay? I don't know which one I'm going to be getting. Okay? But let's say that all the data that I got, the M data that I have, are all this. I have M data that is mu and minus 1. That's all I have. So I don't know whether that's coming from D1 or D2. Okay? I cannot. It's all this same data. And the probability, if you just work it out, there's not much time, for D1 to have all of this, only this, that probability is 99%. It's greater than 99%. So from D1 to get all Z2 is very highly likely probable for both distributions. Okay? Everyone understand what I'm saying? You, what this one? Now, what I'm going to show is that, well, the book shows, this is just, when my A gives you some W, it's going to give me some W, right? That is less than this value, Mu, I've already said it, it's log of 100 divided by 99. So it's close to 0. Mu is close to 0, right? If that's that, then what is this value? The loss over the D1 distribution. You can go through that. That's not too difficult, right? Because you consider the case for Z1 and Z2. Well, it's less than 1 minus mu. Okay? D is 1 minus mu. So, LD1 that. So this is my loss for my prediction W hat. Okay? This is the minimum value if I consider all the values in the hypothesis space. This is the loss, the minimum loss for all the W that I look in the hypothesis space. How big is my hypothesis space? All the W's. Huh? Then that value is going to be quarter mu over 1 minus this value. And if I plug in for mu, log of 1 of 2m and all this, it's always greater than epsilon. It's a mathematical exercise, not very easy. So what is this saying? What is this saying? What is this saying? If it's path learnable, this has to be what? Bounded above by epsilon. But it's at least epsilon. So my algorithm fails. Because I can't make this thing less than epsilon. Okay? Now if my W star is bigger than this value, then it fails on D2. Okay? So, go through this exercise, and this is just to show you that this is not true. Oh, I have a convex function, so it must be path learnable. That is wrong. Okay? That's the message that I want to say. How would you fix this? How would you fix it so that it's path learnable? I'll be talking about this. This is 57, so rather quick. I will talk about this next time and talk about sub-gradient, stochastic gradient, okay? Which is the ultimate algorithm. And you can solve any convex function. Very nice. Okay. Any questions? This is chapter 12. Chapter 12 and 14. There will be a, yes.
Not related to this, but is there a date for the midterm? Yeah.
When is the date for the mid?